Timer got away from me again. didn't mean to interrupt on that. But as you can see, what you're doing is you're getting iron out at very specific temperature range right here, right? And then you heat it up further and remove the other impurities as well. And what comes out of here is essentially pig iron. Pig iron comes out of here, right here. Okay, so the slag is filtered off here. The pure stuff is down below. Now the pig iron only gets you so far, and this is when you see the old blacksmiths and that working on the different metals and that, or the ancient ones that from the Middle Ages and even the Roman time. This is the type of material that they were getting. This is a fairly brittle type of iron, and those swords would break fairly readily. Now, iron is the fourth most common element in Earth's crust. The blast furnace, what we just saw there, produces crude iron. It still has a carbon content of 3.8 to 4.7%, making it rather brittle. When they made the different swords in the Damascus steel and the samurai swords, they would bend them back on themselves several different times so that they would reduce that further, and essentially they were purifying it as they were remolding it each time. Now, the first inexpensive process for the production of steel was the Bessemer process. The key is oxidation with air blown through that molten iron. So you first had to get the molten iron, and so you took your crude iron here, you heated that up, and then you blew oxygen, air, through there, and it uses that oxygen to lower the content to 0.2 to 2% carbon. And sometimes they add other materials to it, chromium and that, to get different grades of steel. Some of them, of course, one's called stainless steel. But it's the Bessemer process that was used to produce all of that, and that was really the foundation of a lot of the industrial age for the last 150 years. Now, however, today most plants use basic oxygen furnace or electric arc furnace, and they can do this because they're mostly using recycled steel scrap. So they're taking what was garbage before, or what is rusted steel that had been produced, and they're taking that as a starting material and then adding some energy to repurify it, and then but it's a lot easier to go through this than to go through this step and then this step to make the steel this way. So when you think about some of the third world countries, and I'm including China in that, this is primarily what they were doing. This is what Japan was doing as well prior to World War II. They were taking our scrap iron and they were doing something along these lines, and so that they were essentially skipping a step or two for a lower cost of steel. This is molten iron being shown as being cast into steel, and it is very hot. This is blister copper. This is obtained from the conversion of copper-containing ore into pure copper. And this is natural silver, and this right here is a vein of silver. Let me know if you happen to see that on your property. I'll be happy to stop by and take a sample or two. And this right here is the resistance of high-temperature superconductors, and this is yttrium, barium, copper, oxygen, right? Note how the resistance falls to 0 at temperatures below 92. This is a very high temperature for something to have 0 resistance. This type of superconductor is what can be used then for either your maglev, magnetic levitation for trains, or for different supercomputer devices, but having a superconductor really simplifies a lot of other electronic processes. This is the magnetic levitron that uses that superconductor to move it along the tracks. And this right here is one that's, you can see the frost on this glass. But this magnet can be levitated above it, okay, because of the superconductive properties. Okay, coordination chemistry of transition metals. This is important for those in the hospital setting because ligands can be formed, monodentate and polydentate ligands. And you'll see what the use is of those shortly. But essentially, metal ions contain partially filled D subshells, right? And so you can get a whole variety of different colors depending upon what the ionic form is of the different materials. So here we're going from scandium to chromium to cobalt to nickel to copper to zinc, okay? And I'm colorblind, but even I can see some color changes on those. And essentially what you're doing is you're having a covalent bond structure that is sharing electrons, and so you have more of them that are then able to give off those different colors. Here you have silver, and you've got two ammonia ones associated with it. Here you've got copper, 4 different ones associated with it. Here you've got cobalt, and you can see you've got 6 hydrogens associated with that. And so the geometry becomes more complex. Because the geometry is more complex, that also means the crystal structure that you're going to be getting out of them can be much more complex, and you can have some fantastic looking stones. This is ethylene diamine, okay? And this is a very important one for a lot of chelating activities involving the human body. This is cobalt right here, and you can see that it forms 3 separate bonds with this type of one. So this is, when we're talking about dentates, we're talking about 1 bite here, 1 bite here, 1 bite here. So the cobalt is taking 3 bites at this particular molecule. This is the hemoglobin, right? Iron. We're all familiar with the hemoglobin. The base is the key one for binding oxygen and transporting oxygen in our bloodstream. And this is what that molecule looks like. This is the hemoglobin out here with the iron complex right in here. Okay? And so this will allow oxygen to be transported in the body. And so you've got this excellent molecule right here that allows us to do that. As a matter of fact, I'll show you another one that's similar a little later on. And essentially for plants, chlorophyll has magnesium here with a similar type of a structure. So platinum right here has these 2 ligands attached to it right here. Okay? And this is a bidentate. In other words, this is 1 molecule over here. This is 1 molecule over here latching onto the platinum. This is the different geometries where you have a pentagon, bipyramidal, square, antiprism, dodecahedral. I'm not going to be testing you on this. I just want you to be aware of what these transition metals are able to achieve in terms of symmetry as well as in terms of ligands. And here's the cobalt again with the water. Here's your chromium, and here's your platinum again. Here's a zinc, okay? And you've got zinc picking up 4 different cyanide ones, right? Here you've got platinum with chlorine as well as ammonia, right? This one right here is interesting because in this particular form, where you've got these 2 next to each other, it's a violet, cis form. If they are opposite each other, it's a green form. Okay? So the same ligands, same metal ion, but a different spatial arrangement gives you very different properties and different colors. In this example, where something is directly across from it, it only has 2 possibilities, it's called the trans. If these were next to each other, it would be called cis. This right here is a cobalt, just to give you an example of one where you've got multiple different ones. You've got 2 hydrogens, 2 chlorines, 2 bromines. So there's only one way that this molecule can exist. If you shifted any of these around, you would have a very different type of structure. Here you have a metal, and you have the same dimethylamines, okay, in each case, and you have mirror images of them. This one, you can't superimpose it on this one right here, okay, but they are mirror images of each other. And this M stands for just about any one of the transition metals. Here you have the cis optical forms. The trans form is just this one form right here, and that's it. And this is the EN right here. This right here just means that this right here is that particular chelate on there. Here's the one for chlorophyll, as I mentioned. There's magnesium, very similar looking to the one that we have for hemoglobin, isn't it? Just a different chemical here, as well as a different, very long chain over here. And here's copper phthalocyanide, which is a blue material. And then you have detergents, paints, fertilizers, all use transition metal catalysts to help prepare them. This right here is a catalytic converter, where you've got 3 different 3-way reduction catalysts, and then out here you've got a 2-way oxidation catalyst. So you do a reduction first, then you do an oxidation to get you those clean emissions. This right here is what a 3-dimensional image of the hemoglobin with 4 protein subunits around it looks like. This right here is EDTA, ethylene diamine tetraamine, okay, to a variety of different hexadentate complexes. And here you have a coordination complex used as drugs. This right here, the reason why they're interesting for us as people in the medical industry is that you can treat heavy metal poisoning by sending these things injecting some of these into a person's bloodstream so that they take the heavy metal out of there so that you no longer have the problems. This right here is just for excess iron, but it also works for other ones. This dimercaptosuccinic acid is useful for capturing other heavy metals that people might ingest if they're working in the industry in different plants that involve heavy metals. This last section is on spectroscopic and magnetic properties, coordinating these things. I'm just going to skim over this. It just shows why we have these type of possibilities possible for the different ones, what the different orientations of the electron clouds are, and what the shifts are going to be between the different ones, so that you have a variety of different ones possible, so that you can have no ligands with a water ligands here and with cyanide ligands here to provide different ranges. The difference in these ranges then means that you're going to be able to get different colors out of them when an electron shifts from one level to another level. Okay? And this just shows you an orientation of that. And this shows you an object is black, it absorbs all color, and it reflects all colors of light is white. An object has a color that if it absorbs it, okay, and so you're looking at that. So white light going in, blue appearing light comes out of it. And so these are partially filled orbitals of chromium, iron, and cobalt, giving you these different colors. So all they're doing with this particular section of the chapter is explaining why you get the different ones for the different metals. Okay, so the hexa aqua iron sulfate and the potassium hexacyanoferrate both contain iron with these D6 ones. But they absorb photons in different ranges, and so they appear different colors. Likewise, copper. Copper 1 tends to be colorless. Okay, copper 2 tends to be brightly colored. And that's the end of that particular chapter. Let me know if you have any questions. I'll be happy to answer them.